Good morning. My name is Oleksandr Maistrenko. I'm a PhD student at Taras Shevchenko National University of Kyiv, and this is the research on influence of chaos on activation functions in Hopfield networks. In deep learning, activation functions play a key role in transmitting signals between layers of neurons. While functions such as sigmoid or hyperbolic tangents have been popular in the past, recent research has emphasized the benefits of using chaos-based activation functions. Chaos-based functions exhibit properties that facilitate faster and more efficient convergence during neural network training. They allow to increase the search area for optimal model parameters, helping to reduce the problem of getting stuck in local minima and providing a more stable learning process. Let the variable x of t denote the activity of the neuron at time t. The state x of t equal to 1 corresponds to the excitation state, and the state x of t equal to -1 corresponds to the inhibition state. Let h of t be an external influence on the neuron, for example, from other neurons. For convenience, we assume that time is discrete. Proposed evolution of an Izhikevich neuron is determined by a dynamical system, which is piecewise linear, piecewise continuous, one-dimensional function. X of t plus L equal to f of x of t and h of t. This family of functions is defined by the function k of h of the slope angle. This dependence must satisfy the following conditions. Parity, k of minus h equal to k of h, monotonic decrease at positive h values, and therefore monotonic increase at negative h values, and k of 0 equal to 2. All these requirements are met by the function k of h equals to 2 divided by 1 plus absolute value of h divided by mu. The above scenario of the transition from order to chaos is observed in many discontinuous or short vertex functions and is called a homoclinic explosion. The chaotic activation function described previously has a drawback. It's non-differentiable for small values of h of t. This drawback can be solved by replacing the linear function with the parametric Bezier function. Such replacement allows to ensure the differentiability of activation functions by fulfilling the condition on the bidirectionality of the equation x of p, where x is the vector of input values and p is the parameters of the Bezier function. The following experiment was conducted to compare the activation functions of the Hopfield networks: a signum, a chaotic Izhikevich activation function, and its differentiable modification. The input data were samples from normal distributions of two classes. The parameters mu and sigma squared were chosen to cover a variety of cases of intersection of the distributions. Training images were built on the training data according to each category of binary classification, and the quality of the models was evaluated on the test data using leave one out validation with the F1 score as the target metric. The null hypothesis is that the activation functions do not affect the model results. The alternative hypothesis is that chaotic activation functions produce better results. Consider the case when the distributions intersect. After 100 experiments using the signum as an activation function, an average F1 score of 0.81 was obtained. Using statistical power, the required number of experiments for the incremental increase to the mean value of the F1 score to be significant can be obtained. Accordingly, at least 23,664 experiments are needed for each group for the z-test to be significant for an increase of at least 1%. 24,000 experiments were conducted for each of the activation functions compared, and calculated F1 score for each experiment. The average value of the F1 score for the experiments with the signal was 0.9, with the chaotic Izhikevich activation function was 0.91, and with the differentiable modification was 0.911. After that, z-tests were performed for each pair of experiments. Both samples with the chaotic functions are statistically significantly different from the sample of experimental signal, but do not have a statistically significant difference between themselves. All of the modification function have better results and can be seen from the statistics. Similarly, experiments with the other parameters of normal distribution were conducted, calculated F1 scores and z-tests. For the experiments with different mathematical expectation, the previous tendency has been preserved. Chaotic functions show a statistically significant improvement over signum, but the differentiable modification shows better results. In the experiments with the same mathematical expectation, all functions showed similar results and have no statistically significant difference. Now let's consider the effectiveness of chaotic activation functions in an experiment with real data. So the examined data had a control group, 29 patients, a group of patients with stage 2 breast cancer, 68 patients, and a group of patients with fibroadenomatosis, 3 patients. The input data for the model were 3-channel RGB samples of fractal kernel dimensions, of buccal epithelium for each patient. These samples differed significantly in the number of elements. Therefore, when preparing the data before training the neural network, and quantiles were calculated for each sample, where n is the number of elements in the smallest sample. Additional data sets were created from the input 3-channel RGB data. The following input data samples were used in the experiments: RGB, red only, green only, blue only, gray channel, and arithmetic mean of 3 channels. To build training images for the Hopfield network, 2 methods of quantile aggregation were used: arithmetic mean and median. At this stage, the training images were sequences of real numbers, but the neurons of the Hopfield network can have only 2 values, 1 or -1. Therefore, additional binarization was applied to the images. Real values were rounded to the 9th decimal place, converted to binary, and concatenated into the final binary portrait. The best results were obtained in the experiments cancer versus fibroadenomatosis. The average value of the F1 score of the 5 best experiments is 0.84. The worst results were obtained in the group of experiments cancer versus healthy and fibroadenomatosis. The average value of the F1 score of the 5 best experiment is 0.57. This can be explained by the distinction of the second class, healthy controls and fibroadenomatosis patients, which when aggregated generated an image that the model could hardly distinguish from cancer patients. Also, the median proved to be a better aggregation for training images. The F1 score is higher in the most experiments, and the best input sample formats are RGB and blue channels, which are present in the top 5 for each group of experiments. The paper demonstrates the advantages of chaotic activation functions of the Hopfield model on the example of experiments with artificial samples from normal distributions and on real data in predicting breast cancer. This area still requires further research and experimentation, and the development and the implementation of new chaotic activation functions may be a promising way to improve deep learning, not only in Hopfield models, but also in alternative algorithms and neural network architectures, and improve results in various tasks. Thank you.